How many of you thought about that thing like this, you know, to calculate the because we say this system is linear, L12 and L21 they are equal, you know. How many of you I will give it to us. Going to give 5 points. If somebody comes tell me how to do it, he doesn't have to tell me how to do it. Just give me kind of hint how this one is done. Because today I'm going to go over it, you know. I think one of the examples I'm going to take an integral and show you how it's going to work out. So let's go to the system with 2 windings. Let's go with the system 2 windings. And when I go over it, I'm going to again come back and ask you how we get to it. This one was only one winding, one source here. They call it single excitation. And you can calculate this one. Now if you have 2 windings, this graphical thing is very difficult to get. It's not easy anymore to do because there is the lambda 1, lambda 2, I1, I2. How I'm going to show it is a little bit difficult. I'm not going to go through the graphical, you know, representation of that. So, if you hear in the question, you know, say a slow moving or, I don't know, fast moving, just related to the constant flux and constant current. You know, just very, very simple. You know, it's not kind of straight, you know, it doesn't mean slow moving. Either it's a constant current or it's a constant flux. So basically, figure out which equation you should use for the calculation of the force and for calculation of the force. So the energy or cold. You know, the systems are not linear. Just to let you know, all the machine designers, there are lots of people who design electrical motors, which they have a torque. Torque is the next topic after course we are going through. We're going to talk about it. They calculate all these things, all this energy or co-energy. Co-energy is a mathematical concept. It's not a physical concept. But they calculate all this co-energy and energy, either one, you know, which we are going to use, with finite element. When they use a finite element, think about electrical motor. Usually they are cylindrical, and there's a moving part inside. And I'm not sure how much you're familiar with finite element. Finite element, it breaks down the whole system. For example, the more the better. 10 million, for example, elements. A small motor, for example, size of 3 times of this, you know, coffee cup, to 10 million, you know, elements. They become very, very small pieces, right? So when they become very small pieces, we can consider them linear. Inside that little piece, we can consider it linear. But if you look at the overall system, is not, because the curve is like this, you know, the VH curve is like this. But by using this technique, they make it linear. They go calculate the energy or co-energy on each element. And after that, they add all of them together. And so now I know how much is the energy, I go take it derivative, you know, I'm going, this is the force. They calculate. Again, look at it. If you look at the Highway 5 from here to Los Angeles, oh, how much, you know, how many left and right you have to make. But if you pick 100 meters of the highway, it's pretty straight, right? Unless you're right in the curve. But even if you're right in the curve, it's still 100 meters, I think it's still going to really look like a straight line, right? My point is, they break it down to the small pieces, which there you can consider it a very good approximation, you know, consider linear. That's the technique they use for this thing. I said, you know, when I said here W and W prime F is equal, usually even in complicated problems, even still for that one, they are equal because we break them down in small pieces. In small pieces, they are linear. But if you look at it overall, they are not. From this element to that element, they are different. WF, W prime F is different from this element to the other element because they are at different point of the curve. Now system with the 2 windings. two-source system. So the story is going to be the same as the single source. You know, either we have a constant flux or we have a constant current. If we have a constant current, we should use the co-energy. If we have a constant flux, we should use the energy, right? So let's assume this one. Again, we remind here WF is the ID lambda, and W prime F is the lambda Gi. Now we have a two system. There is a lambda 1 I1 and there is a lambda 2 I2. Let's see how we're going to solve this. Co-energy. I want to calculate the co-energy. W prime F is going to be equal to. We consider this system first. Think about it. We consider this system is lossless, right? Go back here. One thing I forgot to say. When the system is lossless, let's say we are going to go to LA and there is no friction, there is no air resistance, there is no loss, either in your car or in the road or in the air, right? Theoretically, you can take the Highway 5 to go to the LA, or you can take Highway 8, go over the US and go to the LA, right? If there is no loss, see, keep in mind, if there is no loss, the same amount of energy will be used, right? If there is no loss. So here, look at it here, none of you asked me about this one. Why these two are the same? We calculated. This system, I crossed the loss. Remember, I said W loss is equal to 0. Here I go from here to here, any path I want, I can select. One path was to go through the constant current. One path was to go through the partially constant flux and go there, right? If you like, you can go this way, right? But you can calculate the force from that path. It's very difficult, you know. You have to simplify it as much as you can, right? What I'm saying is you can go this way if you want, right? Because the system is lossless. There is no difference between them. Now the point I'm saying here, I have a system. There is the I1 lambda 1, I2 lambda 2, right? I need to get from this initial value of I1 lambda 1, I2 lambda 2 to the final value of this parameter, right? I can choose any path I want, right? Because the system, I'm going to write something on the board, you may start to ask, why are you going through this path? Why? Because there is no loss. I can go from this point to this point in any way I want, right? There is no difference. You can select another path if you want. So now I want to calculate the co-energy based on this one. So what we should do, you know, I1 lambda 1, they have an initial value. They're going to go to I1 lambda 1 with the final value, right? The same thing, I1 lambda 1, lambda 2. They have an initial value. They're going to end up with the I2 lambda 2 with the final value. Basically, this is the initial value. You are here, right? You are here. You are going to go to this point, right? This is the point 1. This is the point 2, right? We are going to go from this position to that position. We want to know how much co-energy we have, or how much energy we have. Because if we can calculate the energy and co-energy, done. We can calculate the force, right? We can calculate the force. Now, I'm going to put it this way. So, I'm going to say W prime F is equal to lambda 1. This is the path I'm going to select. Lambda 1 di1. Remember, the co-energy is this one, right? Lambda di, right? Lambda 1 di1 when I2 is equal to 0. I'm going to change my I1 from the initial value to the final value, right? When I2 is 0. Can I do that? Maybe in reality, no. Maybe because the system is not lossless. But theoretically, mathematically, yes, I can do that, right? This is one path, one possible path, right? I'm going from this point to that point. First, I'm going to change my current from I1 from 0 to the maximum, to the final value. When the I2 is 0, now I'm going to change the second one. What's going to happen for the second one? Can Can you tell me what's the second one? He said I10. I1 is constant and the final value, right? We keep I1. Why I cannot put it 0? Why? Because see, I moved I1 from here to the final value, right? I cannot put back this one here. You know what I'm saying? I want to put everything over there, right? I want to put everything here. So I kept I2 0. I took my I1 from here to here. So stay here. Don't change anymore. I'm going to go bring my I2 from here to here, right? Do this thing for the average calculation. The equation I put over there. And the definition of that. Then we're going to get that. This is any response. To get the proof of this one. Right? So how about WF? If I want to calculate the WF, how about that? How about that? Can I let me do this here? Can I put this way? I2 d lambda 2 when lambda 1 is equal to 0. I'm going to change lambda 2 first, not lambda 1. Can I do that? Yeah, okay, that's another path, right? But usually we start with the 1 to go through the sequence. Here you can change this one. You can say integral of lambda 2 di2 when I1 is 0, the first term, right? And you can say lambda 1 di1 when I2 is constant. You can do it that way. If you like that way, do it that way. You know what I'm saying? Both of this guy, because this one is going to go from the 0 to I1. This one is going to go 0 to I2, right? Both this one, they should change from the, I put 0 here because I considered initial value is 0. But from the initial value to the final value. From the initial value to final value, right? If you want, you can change this one first. When this one is 0, don't change this one, right? You go there. To be consistent with that one, I'm going to use this one. Then lambda 2 is 0 plus integral of I2 d lambda 2. How much is the force here? Huh? When you consider I1 and I2, both, not just one, right? When you use the co-energy, you treat the current as a constant value, right? How about here? How much is the force here? Right? So I'm going to talk about the torque and we are done with the teaching. I'm going to go through some examples, you know. Today and maybe next week we don't have a class. Thursday, I'm going to go come to session to make sure I can cover the DC machines, you know. I would like to try to solve more examples on these topics, you know, in the force and the magnetic circuits, you know, because this is all the practice, and you know, it gets you better. Now, all we talked here was about what? Linear system, right? In linear system, we have F. Let's go here. When we have a linear system, and we have a rotational. In linear system, we have what? Force. What is the equivalent of force in the rotational system? Force, right? In linear system, we have X. What's the equivalent of X? K, right? Rotation. So, can somebody tell me what's the torque calculation? How it can calculate torque? One what? Meant what? Current system. If there is one current, one constant. If there is two constant. Three, whatever. When I say I constant, I mean all the current we treat them like constant parameter. Or what? Lambda. Okay. Now let's go through more examples. This is all about the torque. But you can see there is lots of calculation. This equation is simple, but there are a lot of calculation. Even simple example. I'll give you one homework tonight. Usually it will be next Tuesday. We'll give you the second one very quick. It's about the torque and this kind of thing. We'll give you the Tuesday after. What date is the Tuesday after? What date is the Tuesday after? Today is the 12, 18, 12 plus 19, 19 plus 26. Yeah, that's it. The Tuesday after will be the DC machine, and the Thursday will be your determination. Midterm will be February 4th, right? But I'm saying the due date for the third homework will be February 2nd. But I will give you solutions now. I'll think about how we can trick down. We can get the solution at least, by Monday. At least we have 3 days. We can get the solution for homework number 3. So let's go another example. We have a system. Lambda 1 is equal to x minus 1 I1 plus x2 I2, and lambda 2 is equal to x I1 3 plus I2. Find a general term for the force. Want to know, we didn't say for which s, but calculate the force for this system. Can somebody tell me how to calculate the force here? Which one do you use? O energy Y. Because the equation is given based on the current, right? The equation is given based on current. So I'm going to go use this equation. So let's calculate the W prime. It's the integral of I1 lambda 1 I1 di1 when I2 is equal to 0. I'm going to calculate this one. Let's call it pi. So how much is this one? This is the lambda one, right? We should calculate lambda 1 when I2 is equal to 0. So basically the second term is how much? 0. So it's going to be x minus 1 to the power times I1